In this video, I'd like to talk about I2C as it relates to hardware design and PCB design. The boards you're seeing here all use not just higher speed interfaces such as USB high speed, DDR memory and so on, but a lot of them contain I2C interfaces. For example, the board on the left hand side, we have an STM32H7 microcontroller in the center, and that controls various registers and the setup for a codec on the left hand side, which contains ADCs and DACs. Similarly, on the top right-hand side, we have this Spartan 7 based DSP board, and that has various I2C interfaces, again to the codec, but also, for example, as storage to an EEPROM, which contains an I2C interface. I2C is incredibly common, even higher speed designs, because it provides a very nice, low-level, typically low-frequency control interface that's very, very easy to implement and to root out. This video I'd like to show you things, for example, how to calculate pull-up resistances, how to route this on a PCB, what you have to pay attention to in terms of capacitances, speeds, specs, and so on. And we'll go through a couple of real-world examples, as well as some data sheets to see how we can implement I2C correctly on our boards, and as you'll see, this is very, very simple. I won't be going into the basics in very much detail regarding I2C. There's a lot of information online, both on YouTube and books as well, introducing you to I2C in case you are unfamiliar. I will assume some familiarity, and I would like to dive into some topics which aren't discussed too much in these videos. If you're interested in more of the firmware side of things, I do have a video on how to write a driver using an STM32 microcontroller, connecting via I2C to an accelerometer in the case of this video, and this is a full process breakdown of that and can also help with understanding I2C. I will also leave various documents in the links in the description below, such as the I2C spec, some various useful application notes, and so on, so you can follow along in your own time. A huge thank you to PCBWay for sponsoring this video. The boards you saw at the beginning of this video were all manufactured and assembled by PCBWay in China, and they did an absolutely outstanding job. I used them both for my personal projects and also quite a few times also for my work projects. They have basic PCB prototype services as well as PCB assembly, which I use as well. But the service I use the most is actually this advanced PCB service where you can really customize the board specs. You can even do HDI, so with buried, blind and micro vias, up to 60 layers, loads and loads of different options, completely custom and completely tailored to your requirements. So I definitely recommend checking that out, as well as their PCB assembly service. Make sure to check them out, and as usual, I'll leave links in the description box below. We'll go over the I2C basics just to start with. Again, this won't be a very in-depth video on the basics. I'd like to discuss a few other things instead. I2C, or I2C, is the short form for inter-integrated circuit, so connectivity between integrated circuits. For example, if we're connecting a microcontroller to a sensor and we want to get, for example, measurement data from that sensor, an option might be I2C or I2C. The nice thing about I2C or I2C is that it's fairly low speed, and that can of course have its advantages as well as disadvantages. It's a bidirectional in quotes interface, and it's very, very easy to implement both on the schematic side of things as well as on the PCB design side of things. On a single I2C interface, we can actually have multiple devices, assuming each peripheral has a unique address. Typically, there's one controller and there's several peripheral devices. This might be, for example, if you look on the right-hand side, a microcontroller with a single I2C interface that hooks up to various peripherals. In this case, this might be sensors, it could be codecs, EEPROMs, and so on. For this interface, we only need two lines. One is called SCL, which is our clock or serial clock, and one is SDA, which is our serial data. Oftentimes, you'll also see I2C referred to as two-wire interface or TWI. So this is really nice. Just with two wires, a clock and a data, we can hook up various peripherals together in a fairly low speed, low bandwidth interface. Again, I2C is predominantly used for control. For example, if I'm interfacing a microcontroller to a codec, I need to set up sample rates and bit depths and so on. I would maybe do that with I2C or SPI. But we can also, for example, connect to low bandwidth sensors, for example, to accelerometers, gyroscopes, magnetometers, and so on, as well as EEPROMs. And there's many, many devices that use I2C. According to the I2C spec, there are three modes, and these modes pretty much relate directly to the clock frequencies. We have standard, which is a clock frequency of up to 100 kHz, fast, a clock frequency up to 400 kHz, and fast plus mode, a clock frequency up to 1000 kHz, so 1 MHz. And there's different hardware requirements depending on what one of these modes we want to use. And of course, the peripherals and our devices, our ICs, need to be capable of using, for example, the fast or fast plus modes if we want to use those. The interesting thing about the I2C interface in comparison, for example, to SPI, is that I2C is an open drain interface. For example, if we look on the right-hand side, this white box with dashed lines around it is a very, very simple drawing of an I2C transceiver, so something you might have at the I/O pin interface of a microcontroller, for example. We have one pin coming out, and that feeds into a receiving buffer, but this interface can also be driven by this NMOS transistor. And now you can see the NMOS transistor is pretty much missing a load, so there's nothing connected to the drain, and therefore this is called an open drain interface. Because it's an open drain interface, if you look to the right-hand side externally, so attaching, for example, to a microcontroller I2C pin or to a sensor, and we'll see more about that later, we have to add a pull-up resistor, one per line. So one pull-up resistor on SDA, one pull-up resistor on SCL. This pull-up resistor needs to have a certain value, and we'll see how to calculate that in just a bit. And it also needs to be pulled up to a valid supply voltage. Valid depends on what peripherals you use, what their logic levels are, power requirements, and so on. And that supply voltage we'll typically call VDD because it's a digital supply voltage. We can see on the right-hand side, on the bottom right, we have this CB capacitor. Now, this is actually not a physical capacitor. It's rather to demonstrate or illustrate that we have some sort of capacitance on the bus. So this is due to our PCB, that's due to traces, the pads, and of course the devices themselves. All of these capacitances add up to our CB bus capacitance. This bus capacitance can't exceed the specified maximum according to the I2C spec, and that depends on what mode you use and so on. So there is a limit to, for example, the length of traces we can use or the maximum number of devices we can have on an I2C bus. If we look at the traces themselves, and I got this from allaboutcircuits.com right at the bottom, we can see we have our clock at the top and our date at the bottom, and this is a very, very simple illustration. But what we can see is that the rise times are these, when we go from a logic low to a logic high, either on the clock or on the data, we can see that's this typical exponential RC response. And this rise time is rather slow in comparison to the fall time, which we can see is this much sharper edge from a logic high to a logic low. So typically a rise time might be in the order of hundreds of nanoseconds, whereas a fall time might be only 5 to 10 nanoseconds, for example. This is something we have to keep in mind. The rise times are predominantly dependent on our pull-up resistance and as well as the bus capacitance, as we'll see in just a second. Again, if you're interested in more detail, I'll leave a link to this in the description below by NXP, user guide UM10204, and that goes through the I2C spec in far greater detail than, of course, we're going to go in this video. So it's 60 pages, preferably read before bedtime. This notion of bus capacitance is quite important also when we come to actually calculating, for example, the pull-up resistor values required, at least the maximum or minimum we can use in a particular design and scenario. The overall bus capacitance is an addition of several different capacitances. For example, we might have a device capacitance. So that might be the controller itself, in addition to any peripheral that's attached to that bus. And that's of course per SDA line and per SCL line, but we'll see that as the overall bus capacitance. Typically, you can approximate that as about 5 to 10 picofarads. We might want to assume worst cases, so typically we'll assume 10 picofarads per device. But if you go to a typical datasheet, you can usually find a range there. So for example, a sensor I use quite a lot is this BMI 088, which is an inertial measurement unit, so it contains accelerometers and gyroscopes made by Bosch. And then simply look for capacitance in the document. We can see table 11 on page 33 lists the electrical specifications of the interface pins, and we can see in general the input capacitance C-in is around 5 picofarads but can be up to 10 picofarads. We can also see the maximum allowed I2C bus and load capacitance, because this device can do either I2C or SPI, is 400 picofarads in this case, so it can drive a load capacitance of up to 400 picofarads. So that's where we might be able to get device capacitances from. So if we have multiple devices on a single I2C interface, we'll have to add those together. In addition, we of course can have trace capacitance. So if we're routing our traces from a host controller to various peripheral devices, that might be a microstrip or stripline trace, and that typically will be a fairly narrow trace, at least compared to power. So let's say, for example, a microstrip trace, so an external layer trace, we have a reference plane directly below. Let's say our trace width is typical of about 0.3 millimeters in width, which is a fairly typical I/O or I2C line trace width. And the thickness of the dielectric, so the height of that trace above a reference plane, for a 4-layer board might be something like 0.1 millimeters. If we assume a typical dielectric constant of about 4.6 and so forth, we will get that our trace has a capacitance of about 2.2 picofarads per centimeter. So this is not very much, but for a 10 centimeter trace, which is quite considerable on modern small circuit boards, that's about 22 picofarads per 10 centimeters. If you'd like to check out how trace parameters affect the capacitance, I'll leave a link to this in the description box below, which is a microstrip capacitance calculator. This is also one I use to calculate this value. So I can type in width, height above the ground, or reference plane, length of the trace, and dielectric constant, and I'll get an output capacitance. That's quite interesting to play around with. They also have strip line, coplanar, and so on. In addition to trace capacitances, device capacitances, and so forth, of course, we also have other capacitances such as stray, pad, if we're going through a connector, if we're going through wire, and so on. And these will add up to form our bus capacitances. Sometimes, of course, this can be quite hard to calculate, and oftentimes you might just want to measure that on the final board itself, or calculate a worst-case estimate, which we'll be using in just a second. All of this bus capacitance is important for us because I2C, also depending on the devices you use, has a maximum allowed capacitances according to the standard. So this table at the bottom is taken from the standard. So again, we have 3 different modes: standard 100 kHz, fast 400 kHz, and fast plus at 1 MHz. And we'll come to the rise times in just a second, but per interface, the standard details a maximum allowed capacitance in picofarads on the bus. And for standard and fast, that's 400 picofarads, and for fast plus, that's 560 picofarads. So very, very crudely speaking, assuming 10 picofarads per device, we could have 40 devices on the bus as a very, very theoretical maximum. Of course, this isn't accounting for non-idealities, extra capacitances, bandwidths, and so on. But it's somewhat of an order of magnitude. We need to know about the bus capacitances because next we'll be looking at how to calculate these pull-up resistor values, again, one per line, one for the SDA and one for the SCL line. Oftentimes we can ballpark the value of a pull-up resistor for an I2C line, especially if we're just talking, for example, to an EEPROM. We're doing fairly infrequent writes and reads and at very, very, very low speeds and low bandwidths. Then we might have typical values you might have seen for a 5-volt system. We might just use a 10K pull-up, or for a 3.3 volt system, we might use a 2.2K pull-up. And these are perfectly fine to use typically if they have suggested values, for example, from a datasheet and so on. You might just want to go with them if you're just connecting a single device or you're not particularly concerned about power consumption and so on. But if you'd like to calculate the pull-up resistor values properly, so to speak, let's see how to do that. First of all, what influences the pull-up resistor value? Well, there's a couple of factors. First of all, the supply voltage. So if we increase the supply voltage, keeping every other parameter constant, typically that will increase the value of the pull-up resistor we want to use. Secondly, the power and current consumption will depend on the pull-up resistor value. So if we increase the pull-up resistor value, typically that will lower the power and current consumption, which might be useful in, for example, battery-powered devices. On the other hand, our interface speed, also dependent on the mode, will determine maybe our maximum minimum values for the pull-up resistor. So if we lower the pull-up resistor value, that might permit a higher interface bandwidth. Lastly, the bus capacitance, as we talked about. So for example, the length of traces, the number of devices on the bus will mean we might have to adjust our pull-up resistor values. So the more capacitance that we have on the bus, the lower we typically have to make our pull-up resistor value. Again, we want pull-up resistors on the SCL and SDA lines, and for a single interface, as a standard, we have the same value for SCL and SDA. Again, we only have one pair of pull-up resistors per interface, and there are exceptions, of course. If we're using, for example, level shifters or repeaters and buffers and so on, which we'll see later, then we will have several sets of pull-up resistors. The placement we'll talk about later on as well, and we'll see that's actually not particularly critical, but there are some standards we might go by. So excuse the lot of text on this slide, but now we want to see how we can actually calculate the pull-up resistor values. Our pull-up resistor, which will be a value we pick later on, has to be between a minimum value, which we can calculate, and a maximum value we can calculate. So to start with, we'll calculate the minimum value. And this is given by this equation at the top left. The pull-up resistor minimum value is the maximum VDD voltage we can expect, so our maximum pull-up voltage, minus VOL max, and all of that divided by IOL. So let's see what those values are. If we go to the I2C bus spec, for example, UM10204 by NXP, and looking at table 10, we can see typical parameters and characteristics of the SDA and SCL lines, including their logic level highs, logic level lows, output currents, and so on. For our equation, we need VDD max, which we just take from our system I/O level voltages, but we need VOL max and IOL. Essentially, all we're doing with this equation is basing this on the output low level and dividing by the permissible current to get our pull-up resistor value. We can see our output level low voltage. So our VOL max, specified at 3 milliamps, sync current and VDD is greater than 2, is 0.4 regardless of standard fast mode or fast mode plus. And our IOL, again, this is where our VOL was specified, and that's at 3 milliamps, so that's the value we will use, at least for standard mode and fast mode, for example. So therefore, as an example, let's say our system I/O voltage is 3.3 volts, and we have a tolerance on that typically, and let's say a very bad case might be plus minus 10%. So our maximum VDD will be 3.3 times 1.1, so adding 10%, so that'll be about 3.63 volts. So that's our VDD max. Our low-level output voltage, again taken from the I2C spec, we saw was 0.4 volts. And our low-level output current, again from the I2C spec for standard and fast mode, was 3 milliamps. Therefore, plugging these values in, so 3.63 minus 0.4 divided by 3 milliamps, gives us a pull-up resistance as a minimum. We shouldn't go below this value of 1.1 kilo ohms for this particular case. So as you can see, if we increase VDD, for example, to 5 volts, our pull-up resistor minimum value will increase. I've also copied in a picture from a Texas Instruments app note, SLVA689. Again, I'll leave links to this in the description box below. And this shows the minimum pull-up resistance versus pull-up reference voltage for voltages greater than 2 volts and voltages less than or equal to 2 volts. And you can see we just have this simple linear slope. Now we've calculated our minimum, we also have to calculate our maximum value. For this, we use this simple approximation formula where the pull-up maximum value is approximately 1.18 times the maximum rise time allowed divided by the bus capacitance. And this value is derived, and I'll leave a link to this in the description box below, to this application note SLVA689. Here we can see the derivation of that formula, and this is just taken from an RC time constant. We have R is our pull-up resistance, C is our bus capacitance, and we have a specified rise time and bus capacitance based on the I2C standard we have, or how many devices we have on the bus, and so on. And from our exponential formula, looking at rise times, we can get this formula and just rearrange to have this constant at the top. Gives us 1.18 times T rise max divided by the bus capacitance. Going back to a previous slide, remembering back to the table at the bottom, again taken from the standard. So our maximum allowed or permissible rise times depend on the I2C mode we use. So standard has a maximum rise time of 1000 nanoseconds, fast 300 nanoseconds, and fast plus 120 nanoseconds. So that's what we will use in these formulae. Therefore, if we're going with standard mode, for example, we see we had our TR max, our rise time max of 1000 nanoseconds. And this also highlights this is a very, very slow interface, at least from a rising edge point of view. Then we can calculate the worst case. And again, the maximum capacitance for standard mode was 400 picofarads. And this is the maximum allowed bus capacitance for standard mode. So let's plug that in at 400 picofarads. So we do 1.18 times 1000 nanoseconds divided by 400 picofarads. And that's approximately 3 kilo ohms. So if we're looking for a worst case, we have to keep our pull-up resistor, in this specific example, between 1.1 kilo ohms and 3 kilo ohms. Now, we will probably, in many cases, we will not get close to 400 picofarads of bus capacitance. Let's say we only have a couple devices on the bus, rather short traces, and then we might only have a bus capacitance of, let's say, 50 picofarads. Plugging that into the formula again, we see our maximum pull-up resistor value then becomes 24 kilo ohms, which is significantly higher than 3 kilo ohms. A higher pull-up resistor value, of course, means lower power consumption, but it does mean a slower rise time, for example. But now we see how we can get a minimum and maximum value. Then the final choice is then, of course, dependent on, for example, power consumptions and worst cases. You might want to leave some margin for the bus capacitance and so on. So unless power consumption is very critical, I would typically go closer minimum calculated pull-up resistor value. So I might put in, let's say, a 1.5 kilo ohm or 2.2 kilo ohm pull-up resistor in this case. We, of course, also have to maybe worry about resistor tolerance, but this is actually not too critical unless you're operating at very, very tight margins. On the right-hand side, again, in the figure from Texas Instruments, figure 3, we can see the maximum pull-up resistance versus the bus capacitance illustrated graphically. You might have already seen repeaters, buffers, and level shifters, but they also exist for I2C devices. We might use a repeater or buffer if we have excess capacitance on the bus, for example, many devices, long traces, or if we're going off-board through a connector, we might want to use a repeater or a buffer. This can help split up this excess capacitance and also help to keep the pull-up values higher to reduce power consumption while also keeping rise times, so to speak, low in quotes. We might also want to use a level shifter in certain times. For example, if you want to ensure I/O voltage level compatibility between devices. You can get I2C level shifters in IC packages, and these might have several channels. And as with repeaters and buffers, the level shifters have to be open drain capable. If you want a really very basic, fairly low speed, single channel level shifter, I can recommend the circuit on the bottom right, which is a single NFET transistor with pull-ups, so to speak, either side. And that can voltage translate, and this is a bidirectional level shifter, the lower voltage on the left, so for example 3.3 volts, and the higher voltage on the right, so at 5 volts. This is a circuit I use many times if I want to do something fairly cost effective, if I'm maybe already using transistors in the design, and I don't want to add an additional IC. Something like this for standard mode works very well. Having a quick look at Mouser, going to, for example, the Logic IC translation voltage level section, there are many different options we can have, for example, for I2C or open drain bidirectional level shifters. So I've just picked out a fairly random one here, PCA 9601. We have to make sure that it's bidirectional and it can handle open drain buffers. We can also see what capacitances it can handle and so forth. And typically then a connection might be like so. We can use multiples of these buffers. We do need pull-up resistors in between every time we, so to speak, jump from one side to the other side of a buffer, as you see here, and this is always outlined in datasheets. Another option other than buffers is also using a multiplexer, for example, a PCA 9547. This happens to be an 8-channel I2C multiplexer. And what this does, it can actually take a single SCL and SDA I2C interface and multiplex that out or send that out to various different, in this case, up to 8 pairs of I2C interfaces in case, for example, you have multiple devices on an interface that share the same address. So, for example, you have 8 sensors for which you can't change the address. You might want to use one of these multiplexers. So on a single I2C bus seen by, for example, the host controller, we can attach 8 of the same peripherals, for example. There are these options as well, and typically these multiplexers might contain buffers as well and might help with level shifting and so forth. Before we move on to PCB design, I'd like to show some schematic design or circuit design considerations when you're including I2C into one of your designs. As we saw, it's a very, very straightforward, simple interface, but there are a few things you should pay attention to, especially if you haven't done this before. The first thing being, as we just saw also with the multiplexer, is that we can't have peripherals with the same address on the same bus. So if we're using a simple single I2C interface and we're hooking up multiple of the same sensors or peripherals, and each I2C device will have its own address that it responds to, if these addresses are the same, we get some sort of bus contention and this simply won't work. Therefore, an option might be to use an additional separate bus, but that, of course, if you're using many, many different sensors, splitting up your I2C bus into many different interfaces might not make sense. But there are devices, for example, the EEPROM on the right-hand side, would have dedicated hardware address select pins. So A0, A1, A2 on the right-hand side can be used to configure bits of the I2C address of this device. Additionally, there are parts and devices where the part number itself indicates a device variant where you might have a different I2C address depending on which part number you choose. So that might be an option as well. As a simple example here, let's say we have a microcontroller hooked up with a single I2C interface, so SDA and SCL. We have a single set of pull-up resistors to 3.3 volts. We're connecting up 2 EEPROMs and a sensor, for example, a magnetometer. And this is a very, very crude example. It was just created for this specific video. We can see our EEPROMs have A0, A1, A2. So I've tied one EEPROM all to ground, and the other EEPROM, I've tied one bit or one address select bit to 3.3 volts. And therefore, I can distinguish between the addresses of the EEPROM of these 2 EEPROMs. And then we have the magnetometer. And of course, we should check the datasheet if the addresses are indeed different if we are sharing the same I2C bus. Otherwise, you can, of course, use a multiplexer or split them up across many different buses. What we also have to take care of is, of course, VDD and VDD-IO levels. Make sure you're staying within the recommended operating conditions. Make sure, depending on your pull-up resistor values, that might shift the logic levels a bit. And of course, there's also a mode select pin oftentimes. So for example, on the bottom right, the magnetometer, you see we have this CS or this chip select pin. Now in SBI mode, that actually serves as the chip select pin, but if we want to select I2C mode, we have to pull this pin high to the logic level high at startup. So that's why pin 3 in this case is pulled up to 3.3 volts to select I2C. And that's again written in the datasheet, so make sure you check that out in the device and not just simply hook up SDA and SCL. Make sure to check if there is, for example, a hardware mode select pin. What also we have to pay attention to is, of course, the required speeds and required bandwidths. If we require a very fast interface, we might have to reduce our rise times, and that typically means decreasing the pull-up resistor values, so staying closer to the minimum values we calculated when we calculated our pull-up resistor values. We might also want to use less devices on the same bus and split our devices up over several buses. That means we might be able to access these devices in parallel. If our host, of course, allows that, we get less capacitance on the bus and so on. For battery-powered applications or where we want really low power applications, we might want to increase the pull-up resistor values because that reduces the power and current consumption, but then again, we might have a trade-off with bandwidth as well. When we're going off-board via connector, again, we might want to use a buffer or a repeater, especially if it's a very long cable. We want to add some filtering in terms of pi filters, and of course, we might want to add ground returns on the connector next to SCL and SDA, so we minimize interference and noise issues. A common problem with I2C lastly is I2C bus lockup. If there's some sort of contention on the device, one device malfunctions, if we're sharing a same I2C bus, that might lock up the SDA and SCL lines, and we can't use that interface anymore, so all the other devices that are sitting on that same interface are not accessible anymore. Therefore, I'd strongly recommend either to split the devices up on several buses, or include a capability to reset the devices, be that with a dedicated reset pin, if your device has that, or being able to cycle power to just those I2C peripherals, for example. Lastly, looking at PCB design, and we'll go through some real-world examples as well. I2C, as you saw from a schematic point of view, is very, very straightforward, and it almost seems like it's even more straightforward from a PCB design point of view. Again, it's a fairly low rise and low fall time interface, so it's fairly forgiving. All we have to do, as usual, is follow good PCB design practices. So that makes sure our I2C SCL and SDA lines, route them above a reference plane, ground ideally, or a plane that has the same voltage as, for example, the I2C interface. We don't want to cross splits. Keep distance between the SCL and SDA lines, so don't hug them together or route them as if they were a differential pair. And keep space between the SCL and SDA lines and any other copper, so that's traces, power nets, components, the board edges, and so on. And that's our typical 3H rule, so keep a spacing of at least 3 times the dielectric thickness to the closest reference plane away from any other components and so forth. Keep traces as short as possible. Again, this is due to capacitance, but more due to crosstalk, emissions, noise, and so on. Don't make the traces excessively wide either, because making the traces wider typically increases the capacitance, which is unnecessary. We're not carrying any significant amount of current or power in these traces. If possible, and I'll show you an example of this, don't route with stubs, so some sort of star configuration, if you have multiple devices on a single interface, but rather route through the devices, and we'll see that in just a bit. The pull-up location actually isn't terribly critical. It's typically, however, recommended to place that close to the controlling device, so our host, so to speak. Control impedance, is that necessary? Not really. Again, rise and fall times are very slow unless you have very, very long traces, but by then you might be running into other problems anyway. So I wouldn't route them as controlled impedance traces unless you already have controlled impedance in your design anyway. So if you're routing other signals with 50 ohms, then you might as well route your I2C signals at the same trace widths and same parameters. Termination, that isn't needed either. Pull-up resistors here aren't termination resistors, and we typically don't use termination resistors on the I2C lines. So now let's go over and look at some real PCB designs and some demos and see how we might route this out. To start off with, let's look at this actual real-world PCB. So this is one that I had manufactured by PCBWay, which we saw at the start of the video. This is an audio digital signal processing board for guitar, contains an STM32H7 microcontroller, which interfaces via I2S to this codec, and this has this analog front end, so inputs and outputs to the ADCs and DACs. But I also have to set up this codec via I2C, which is connected to, in this case, my controller, the STM32H7 microcontroller. I don't just have this fairly high bandwidth I2S interface, so for sound, I also have this control interface I2C between U200 and U300 between the microcontroller and the codec. If you go to 2D view, I've highlighted that with these blue traces. I have my I2C lines, SCL and SDA coming out of my host, my controller. I'm trying to keep them as short as possible into my codec, which is down here, again into the SCL and SDA lines. There's nothing particularly special going on here. Closer to the controller, I've placed my pull-up resistors, but again, the location isn't critical. I'm routing through with the clock and data lines, but on the other side, the pull-ups to my system level VDD voltage, I have short white traces with a via going to a power poor, which is on the opposite side of the board. What I could also do is I move my pull-up resistor like so, connect my clock line like this, and then do this kind of stub routing, but this is definitely not what we want. Although for I2C, this probably won't make much of a difference, the ideal routing is through the pull-up resistors rather than having these little branches and these little stubs. The routing itself, I'm just using traces that I use for other signals anyway, so if this is controlled impedance or not, I'm using the same width of traces, and as soon as I come out of, for example, the microcontroller pads up here, instead of sticking close to the other trace like this, as soon as I can, I branch away and I give myself space between clock and data like so. Also, I don't want to route close to other components. I want to give myself space within the I2C interface, but also between other components as well. And I maintain that clearance and I maintain that space as much as I can until I have to go into the codec like so. So where I have to neck down, I do, but as soon as I have space, I space them out. The I2C traces in this case are on layer 1, and on my reference below is a solid ground poor, ground plane, and you can see it's uninterrupted. I'm keeping clear of voids, and I'm not crossing any splits like so. Again, there's not particularly much you have to pay attention to other than typical good PCB design practices, and this is fairly straightforward. As another simple example, I've drawn up a very quick schematic. This is in no way complete. I've just popped on a microcontroller and a couple I2C devices just so we can see how we might do routing when we have many of these devices on a single I2C bus. Now, looking at the very simple PCB, none of this is routed out. This is just for demonstration purposes. We have the microcontroller, our host, so to speak, on the left-hand side, and we want to connect a single I2C bus to U2, U3, and U4, which are two EEPROMs, and a magnetometer. Again, this is a very, very simple and rather crude example. I just want to show you how you might go about routing I2C, and actually that the routing itself doesn't matter too much. This is a two-layer board just for demonstration purposes, so the bottom layer is completely filled with a ground copper core, and the top will do our signal routing, just as a very basic demo. So if I go to 2D view, you can see the blue highlighted nets are our I2C, that is SDA and SCL, and we want to route essentially between our microcontroller to these various ICs on the right-hand side. The first thing I typically do might be to somewhat roughly place the location of my pull-out resistors. And you can see here, I've got these two 5.1K pull-out resistors in this example. Again, depends on the speeds and what we talked about near the start of this video. Typically, you might want to place them centrally to all of these devices, but oftentimes the actual location doesn't really matter too much. I prefer to put it close to, for example, the host controller, so close to, for example, in this case, the MCU. Now, there's a couple ways of routing this. If we have multiple devices, if we just have a single device, we saw that just in the codec example. But for multiple devices, what I take, let's say the SDA trace, and I just want to make that a typical signal trace width. So I don't want to do something excessive, for example, 0.5 millimeters or something that looks like a power trace. I want to make a fairly decently sized, and that of course depends on your board stack up parameters and so on, but something similar to, for example, the pad width of the MCU, so 0.25, 0.3 millimeters. I route directly out and into my SDA pull-up. From there, I have a couple options with this SDA. What I could do is this kind of branch routing. So if I just route up to the top SDA of the magnetometer, I can branch off and route, for example, into one of the EEPROM SDAs. I could branch off below and into the bottom EEPROM like so. And typically, for higher speed interfaces and buses, I wouldn't really recommend this branch topology, but honestly for I2C, especially for these kind of short trace lengths, it really doesn't matter very much. Alternatively, if you don't like this branch topology, what we could do is kind of route through the components. So we start again from the host controller through the pull-up, and let's say we route down to the bottom EEPROM first, then we can come out of the bottom EEPROM, route into the top EEPROM like so. So we're following this path through the IC, so to speak, and out of the top EEPROM into the magnetometer. So rather than branches, so to speak, we're routing through. So that is an option, of course, as well. And we could do something similar for the SCL trace. As soon as I come out of the SCL pad, I don't want to hug this SDA trace. I want to break away, again, for crosstalk, noise reasons, and so on. So I want to break away as soon as I can from the SDA trace into my SCL pull-up, and then I can do a similar routing methodology. I'm keeping space between SCL and SDA at all times into the SCL pad, and then I could, for example, do a short section underneath the component and route like so into the next one, give myself some space between components, traces, and so forth, and then I could, for example, route the last trace to the top like so. So I might have to route around the component, which again, for I2C, it doesn't really matter too much. It's one of a lower priority signal, typically in a design. What you still want to do is keep distance, maintain spacing, try to keep your traces as short as you can. But again, from personal experience, it doesn't really matter too much if you route through the components or if you really do these branches. If you do these branches, I'd aim to keep the branches short. That's just a general guideline. Again, you can be pretty free with I2C because they're very, very slow rise times. And typically, unless you have very, very long traces, you're very, very flexible with the routing. Make sure, keep your traces short, space them far enough apart, route through pull-out resistors, and keep distance between other components, traces, board edges, and so on. On the other side of the pull-out resistor, if you have an internal power plane or you're using polygon pores, all I would do is route out a wide trace, so a power trace, short and wide, and place a via close to the pad. For example, like so, I can copy that structure and place it, for example, at the SCL pull-up, so signal traces versus these power traces from the pull-up. So a very, very crude and simple example. Again, you can either route as a branch or through the components if you have multiple of these ICs. Just keep them short if you can. Thank you very much for watching this video. I hope it was useful and I hope it gave you some pointers on how to implement I2C in your own designs, both from a schematic and a PCB design aspect, looking at pull-up resistors, bus capacitances, where to find necessary information on how to implement I2C in your own designs. If you like the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest hardware design, PCB design, and general electronics videos. Thanks again, and I hope to see you in the next video. Bye-bye.